Welcome everybody, it's Ramchandra from CIVIL-MECH-MATHS CONCEPTS. I will discuss about bending stresses. Welcome everybody, it's Ramchandra from CIVIL-MECH-MATHS CONCEPTS channel. CIVIL-MECH-MATHS CONCEPTS channel. And I have released 9 videos on structural analysis, and all the 9 videos are different from one another, and the forces were discussed in early lectures, and the moments and shear force definitions were discussed in the mid of the lectures, and in the 7th to 10th lecture, 9th lecture, we have discussed about the beam theory, in which M by I is equal to sigma by y is equal to E by R, where M is the bending moment, I is the moment of inertia of the shape, sigma is the bending stress, and y is the distance from the neutral axis, and E is the Young's modulus, and R is the radius of curvature. This, for finding this distance from neutral axis, we have to find out the center of gravity, yc or y bar, and from that we have to find the distance from the neutral axis. Center of gravity position is nothing but neutral axis position, that you please remember. And also M is the bending moment, which we can find out from the loads applied on the beam, and I is the critical value which is to be found out, that is moment of inertia or second moment of area. The critical part of this total calculation is finding the moment of inertia or second moment of area of the shape given. Now, from that we will find out sigma. Sigma is equal to, that is applied stress at a particular point, is equal to my by I. From center of gravity we will get the value of y, and from the loading we will get the value of bending moment, and for a particular shape, from the geometry of the beam used, we will get the value of moment of inertia. This calculation is very crucial in finding the bending moment applied stress due to bending moment. Similarly, there will be a shear stress that I will be discussing in the following lectures. One is bending stress, that is due to the bending moment, and another is shear stress, that is due to the shear force. I have already discussed in my earlier lectures about the calculation of the shear force. For example, let us say we have one simply supported beam like this, and there is an uniformly distributed load with W, or we can say Q, newtons per meter. Then we will have shear force and bending moment in the form of, this is RA, reaction at support A, reaction at support B. I have already shown you how to find out the reactions at support A and support B, and what is the sign convention, that also I have discussed earlier. Then we will say the shear force, the bending moment diagram will be like this. It will be maximum at the center, Don't worry about the sign convention now. Try to understand what I am explaining you. And this is the shear force diagram. This is BMD. This is shear force SFD, shear force diagram. And wherever the value of bending moment is the maximum, BM maximum, shear force will be minimum or 0. You just see shear force in shear force diagram, shear force is changing the direction from positive to negative or negative to positive, whatever sign convention you follow. There is no harm in following any sign convention, but it should be uniform everywhere. That you should keep in mind. Throughout your study, the sign convention should be uniform. Like I have explained you in my previous classes, you please remember, see the video. The sign convention will be like this. This is the shear force. And when shear force acts like this, what happens? There will be either sagging movement or hogging movement. The shear force can be like this or like this. These are the two combinations we get for shear force and bending moment. Sign convention, which I have explained in my previous classes. You please follow that sign convention. Now, here in this lecture, it's not about the sign convention, it is about understanding the BMD and SFD. Understanding the bending stress and shear stress. Now, bending stress is due to BMD. Here we get the value of M. I for the particular shape is known, that is constant. And at this particular point, let us say, this is the point where bending moment is maximum. That is M is maximum. I is known. Then that particular shape, let us say it is a rectangular shape. Now, let me show you what happens. It is without load. Originally this is the shape, and if load is applied, when load is applied, what happens? It bends like this. It bends like this. This theory I have already explained in my previous videos. You please see those videos to get the better understanding of this bending moment. Because of the bending moment, what happened? That beam is bent and it is concave, upper one, and lower one is convex. That means lower one is spread and upper one is, what you feel, it is reduced. The length is reduced. Here you see this is the neutral axis. Along the neutral axis, the length of the fiber, this is the height, beam height. This is the H. This is the beam width B. What we have considered here is rectangular beam. What is the I? I is equal to BH cube by 3 or BH cube by 12 as we consider x axis and center of gravity. These details also you can view my previous lectures and understand. In my previous lectures, I have explained everything. This is for ICG. For your clarity, I will tell you this is IXX. if this is XX and this is CG. I don't want to go into these simple definitions because I have already explained. Now let us move forward. Now this is the neutral axis, and this neutral axis, it will be straight. For example, this is the B and H like this, original. Let us draw each nearby. This is the neutral axis. This neutral axis length, whatever is there here, the same length will be here, maybe in little curved form. This is before bending. This is after bending. Before bending, the length. This is the length. I am not talking about the beam length. I am talking about the cross section. Let us say we will call it as a B, width. This B, whatever is here, the same B is here. I am seeing as a cross section. You see the cross section. When you see this portion cross section only, then this is B. This is the cross section. It looks like this. This is the cross section. When you say this is B, this is H, I have just only, for your convenience, I made it little bit magnified. This is the cross section. This is the cross section. This length and this length is same. That means there is no increase in the length. Here there is an increase in length. Here there is a decrease in length. Whenever there is a decrease in length, that is negative strain. What is strain? From our definitions, strain is equal to elongation. Elongation, don't think that elongation is always positive. Elongation or change in length divided by original length, that is the strain. Now you just see here, let us see, elongation is in the portion, let us say neutral axis, elongation change in original minus, elongation is nothing but original, difference between original minus elongated length or new length, elongated or shortened length, new length. Put it in absolute values, divided by original. That is equal to, what is the original length? That is B. Along the neutral axis, what is the elongated length? That is the new length. Let us say this one as new length. Instead of elongated length, we can say it is new length. New length can be positive or negative. The difference should be taken. Elongated length and new length is B minus B. Because along the neutral axis, the definition, please remember, there is no change in the width of the beam. Length means it is not the beam length. Cross-sectional length. In cross-sectional length, that is beam width. That is B minus B. Original is B. That is equal to 0 by B. That is equal to 0. That means from this we can say strain along the neutral axis is equal to 0. If the length is reduced, what happens? If the length is reduced, strain will be, strain is equal to negative if B is reduced from original value. It may be that strain quantity may be quantitatively, it may not have any sign, but strain will have a sign whenever there is a reduction in the original value of breadth or length, which we have used original. Strain is equal to positive if nu b, let us call nu b is increased value from original. That means positive strain is called as tensile strain, negative strain is equal to compressive strain. Even though I have explained the sign convention of bending moment and shear force in the previous classes, I want to again brief you for few minutes the sign convention. Please try to understand. Please put it in your mind, this one. Because out of practice I have drawn this SFD and BMD correctly, but whenever you draw the SFD and BMD, these values will be positive whenever there is shear force like this. Shear force cannot be single. It will have two-way, and bending moment is like this. This is positive. And what is negative? Negative is negative when shear force acts like this, opposite to whatever we have assumed initially. Many books follow this one, and there is no particular rule that you should follow this one only. It will be up to you. And if you follow this sign convention, it will be convenient for you wherever you refer to many books for various examples and various problem solving, and in the examination also. But please follow one particular sign convention, you apply that only. Like this, in the last example what we have shown, you just see, this is what is the problem in the last example. This is what it is. It is RA. This is what we have assumed. This is RB. Because RA on the left hand side is upwards. It is W, because W, newtons per minute, UDL, is working downwards. Then definitely RA and RB should counter that. Supports will counter the loads, so that beam will not be under any what you call movement. For static equilibrium, the upward forces is equal to downward forces. That is as per static equilibrium. Now you say, what are the downward forces? RA plus RB. What are the upward? It is RA plus RB is equal to downward force is equal to W into L. Let us say this is the length of the beam. This is the length of the beam, WL. From uniformity or from symmetry, RA is equal to RB. Due to symmetry, that means RA is equal to WL by 2. This will be WL by 2. That will be acting upwards. And here also, right side upwards, WL by 2. And what is the sign convention? When shear force acts on left hand side upwards, it is positive, it should be taken as positive. And when it acts upwards on the right hand side, this should be negative. This is for SFD. Values we know. As per sign convention, this is plus, right side it is minus. Now let us come to bending moment. Bending moment, if you take a x here at a distance of x, what is the mx value? Mx is equal to RA is acting in the upward, left hand side upwards, and RB movement is also acting in the upward direction. That means here bending moment, this is for SFD, bending moment is positive because it is acting like this. This is mx is acting like this, and RB is also acting like this, upwards. That means here also it is plus, that is BMD. Now in toto, this first one is accepted. First one, SFD is positive on the left hand side, and it goes like this. Right hand side it will be negative, here it is positive, here it is negative, and bending moment will be this is the point where BM is maximum. Here it is 0, bending moment at the simply supported supports, it will be 0. This is the SFD and this is the BMD. BMD across the length it is positive, SFD changes its. When something changes its sign, SFD changes its sign, implies bending moment is maximum at that point. First, whenever bending moment is equal to 0, that implies shear force SF is equal to maximum. Please remember these two rules. With this point in view, let us try to develop simple concept so that why we are studying this moment of inertia. Now let us say the original shape of the beam is like this. Cross section, it is not about the length, it is original cross section is like this. This is B, this is H, and what will be the bent cross section? The bent cross section, let us say it is bent like this. it is bent like this at the bottom. Original cross section is bent like this. Now you think what's happened at the top. On the top, what is happening? Because of the loading, we have seen that bending moment, it acts like this on left hand side and right hand side. Here we are talking about the bending moments. This bending moment, from the sign convention, M is equal to positive. You agree? You see the sign convention here? What is the sign convention? When bending moment on both the sides, left hand side and right hand side, works towards top, then it is bending moment is positive. Then there is one, this is the neutral axis. Neutral axis is at a height of h by 2. That we have seen in the previous examples. It is a rectangular beam. This neutral axis will be like this. This is the neutral axis. And when bending moment is acting towards the top, what happens? As far as strain is concerned, here the strain will be compressive, negative strain, because the fiber length is reduced or B is reduced. The new B is, this is, let us say, B dash, this is B double dash, this is B. B dash is less than B and B double dash is greater than B. Please try to understand. At neutral axis, it remains the same B. Whenever B dash is less than B, that represents a strain in negative strain. Whenever B double dash is greater than B, this is positive strain. Then here it what happens? Next stage what we'll see, this particular beam. Please try to understand this clearly. Let us not waste time in repeating the same things again and again. This is the neutral axis. And above the neutral axis, because of the negative strain, because fibers are compacted, here what is happening? Fibers are getting compacted. When the fibers will get compacted, the force will be towards the surface. When the fibers get, let us say, when the fibers get, you please see, expanded, here expansion, here it is positive, the forces will pull. Here forces on top, force is compressive. Here force is pulling. It is pushing force. Please try to understand this clearly. Pushing force. Pulling force is tensile. There is a compression on the top, there is a tension in the bottom. for the particular loading. If the loading is like this, if the loading is like this, there will be negative at the top, negative strain, and positive strain at the bottom, because it will be like this. The cross section, new cross section, new cross section. This is negative, this is positive. Now, this is when movement is like this. When movement is positive, this is M is positive towards the top. This is the stress diagram, stress distribution diagram. How will be the strain? Strain will be like this. Strain will be like this. Compression means negative strain, this is positive strain. It is negative, it is positive. This is strain diagram. That means along the neutral axis, strain, the first point is along the neutral axis, strain is equal to 0. The length of the fiber is equal to constant. There is no change in the length for this type of loading, and stress is also 0. This is at neutral axis center of gravity. This is the importance of finding the center of gravity of a particular beam. Then we will come to know the compressive stresses, compressive strains, tensile stresses and tensile strains. Then from the code we will get sigma A load, the maximum tensile or compressive stresses as calculated above or compared with code values. And for example, my point is here. This is YC. My point is here. Here I want to find out at a point P. At a point P, I want to find out the stress, and I want to know whether it is a compressive stress or a tensile stress. From the diagram we will know that it is a compressive stress, and this let us say Y. That means I know Y. In the beam theory equation, what is beam theory equation? M by I is equal to sigma by Y is equal to E by R, which implies, as per beam theory, sigma applied is equal to my by I. I for a particular shape is constant. We are calculating for different shapes. M as per the loading it is constant. Then what is Y? Y is the position where we want to find the stress. This is the bent beam, let us say. After loading, before loading it was a perfect rectangle, but after loading it is not a perfect rectangle. Now let us say this is my neutral axis. Why I am discussing again and again and explaining, the reason is that it is a very important topic to be known. And I want to know at a point P what is sigma P. Sigma P is equal to, this is the distance from neutral axis, YP. That means YP at a point into M divided by I. M is known from the bending moment diagram, maximum M. And I is the moment of inertia from the shape we can find out. And Yp is the point at which we want to find out the stress. That means with this equation, we are able to get the value of stress at a particular point. Then what is sigma maximum? That is equal to Y maximum into M maximum divided by I. Please remember this. The maximum applied stress can be calculated by this equation. M maximum can be found out from the loading. I is constant for a given shape, and Y maximum is the distance of a particular fiber, the maximum fiber where it is extreme fiber from the neutral axis, that is Y maximum. Then we will get the maximum shear stress as maximum bending stress applied at a particular point. M maximum known from loading, I known from given geometry, Y maximum the distance between neutral axis and the extreme fiber. Here extreme fiber is here, here the extreme fiber is this, here the extreme fiber is this. You see, what is Y maximum? This is Y maximum. Once you know Y maximum for the given geometry, for the fiber, and M maximum and I, we can find out the stress, maximum stress applied at that particular point. Then can we write like this? M maximum divided by I by Y. Or if you forget all these maximum subscript, you can write sigma is equal to M by I by Y with regular definitions. This is M by Z. Very, very, very important formula. Please remember this. If I is known for a shape, Y is known, Y max is known, then I by Y is equal to Z. Z is equal to called as section modulus. Section modulus. That means by finding the section modulus and bending moment, we can find out the applied stress at that particular point. Section modulus for a rectangular beam of B width and depth of the beam, let us say D. I am talking about the cross section of the beam. Then what is I? I is equal to BD cube by 12, whereas Y max is equal to D by 2 from the neutral axis to the extreme fiber. Neutral axis to the extreme fiber. This neutral axis is at YC. Then Y max is equal to distance between the extreme fiber and the neutral axis, that is D by 2. This D by 2 is equal to Y max. Once we know this, that means from the extreme fiber on the bottom or top, if you find out the distance between the neutral axis and the extreme fiber, that is D by 2 for the given geometry, I is known, then Z is equal to, for rectangular shape, rectangular cross section beam, BD cube by 12 whole divided by D by 2, that is equal to BD square by 6. This is very, very important, because maximum beams used either in C shape, L shape, I shape or T shape, the maximum used are rectangle. That means the section modulus of a rectangular beam is BD square by 6. What are the units? Section modulus units are cubic meter in SI units. This is about the section modulus. Now, till now, we have developed a concept of section modulus and the importance of neutral axis, extreme fiber length, and also SFD and BMD, the SFD BMD sign convention. Now, there can be a question. There can be a question in examinations like this. What will be the variation of strength of a beam on the basis of the section modulus? How do you answer this? I am asking the relation between the strength of the beam and the section modulus. What code says? Code says sigma maximum allowed. Sigma maximum applied should be less than sigma maximum allowed. This is the requirement of the code. And usual factor of safety are applied. I am not talking about the factor of safeties now. Just try to understand the concept. Now, what is the maximum applied? The sigma applied or found out at a particular point is sigma maximum applied. We are talking about the maximum fiber distance. Then this will be m by z max, section modulus maximum. Now, if sigma maximum applied is equal to m by z max, from this what we can derive about the strength of the beam? Bending moment as per the loading is constant. Sigma is directly proportional to 1 by z. Do you agree this? Bending stress is directly proportional to 1 by z. Because m by I is equal to sigma by y. That implies sigma is equal to my by I. That is equal to m by z. This is the basic formula. This is the relation. When the section modulus increases, the stress at that particular point is reduced. And when z increases, stress at that maximum stress applied can be applied. Reduces. Or else maximum stress not can be applied, maximum stress applied reduces. That means a beam having a higher section modulus for the same loading, the sigma applied reduces. Sigma applied reduces means sigma applied, for example, please try to understand this concept is very, very important. For example, my z is equal to 100 cubic meter. My sigma applied at 100 cubic meter is 10 pascals. Let me say 10 kPa. This is sigma applied. And if my z is equal to 200 cubic meter, then sigma applied will be correspondingly reduced. It will become 5 kPa. My sigma allowed is equal to, let me say, sigma allowed is equal to 9 kPa. In the first case where z is equal to 100 cubic meter, my sigma applied is 10 kPa. That means that is the stress applied there when z is equal to 100 cubic meter. That means in the first case sigma allowed will not change, 9 kPa, that is from, whereas sigma applied stress at a particular point is 10 kPa. That implies design not accepted, as sigma applied is greater than sigma allowed. Please, this you please remember. Don't get confused in the examination. Greater than, less than. And second, Second case, sigma allowed is equal to 5 kPa, 9 kPa. This will not change. Whereas because of the increased Z, here Z is increased. Z increased. Because of the increased Z, sigma applied is equal to 5 kPa. Because sigma applied is less than sigma allowed. Sigma applied is less than sigma allowed. That means it is accepted. When you get the lesser stresses in a beam, when you get the applied stresses, lesser applied stresses at a particular point for the same loading, the strength of the beam is more. That means whenever section modulus increases, the strength of the beam increases, or the stresses calculated at that particular point decrease. That means finally what we have concluded? Please remember this, very important. Z increase implies strength. Increase implies sigma applied. I am not talking about allowed. Allowed is always constant as per the code. Sigma applied decreases, and the vice versa. Please remember this. Very, very important. There can be one, at least we can expect 3 to 4. We can derive 3 to 4 objective questions from it in multiple choice. There can be a chance that the question can be asked on this. Very, very important. And this is how we can get the valuable information of a particular beam. Now, you just see, we got all this. Now, let us assume the dimensions of the L beam given. Let us say the dimensions of the L beam given this is web part. Let us say this is vertical part 10 mm thickness, and let us say up to this is 100 mm, and this is 100 mm, and this is, let us say, 50 mm. Sorry, this is 50 mm, let us say, because it is looking shorter than length. Let us say this is 50 mm, and the thickness, let us say both are same, 10 mm. This we can say L-shaped beams or angles are used whenever perpendicular angle, both sides of the trusses or members of the truss are to be aligned as per the design. This is a perpendicular angle. Now, because we have discussed about the stresses and the meanings of the stresses. Now, I feel it is time for us to close for today, and this L beam will try to calculate. Homework I will give. Calculate moment of inertia and center of gravity of L beam given, L angle, otherwise we will say L angle given. Find both center of gravity x coordinate and also y coordinate. And ICG. This you do it as a homework. If you are unable to do it, please comment in the link provided and I try to solve it. This is what is the importance of bending stresses in the beam. From the bending stresses, we will find out the exact value of the failure point, so that whenever there is a failure is occurred, we can change the section modulus and redesign the beam, so that in the physical sense at site the structure will not fail. We will do the calculations as per the code with the factor of safety, and then we will go for the sigma applied and we will compare the sigma applied and sigma allowed by using the factor of safety, and then we will come to conclusion whether the section modulus of this beam has to be increased or decreased. Too much increase in the size of the section modulus will also hamper the cost of the structure, and a lesser section modulus means the applied stress will be more where failure may occur. Another point we can say, sigma applied if it increases beyond sigma allowed with due factor of safety, that implies failure. Ultimately, we have to ensure that our structure will not fail. That is the structural engineer's responsibility. And it's Ramachandra from CIVIL-MECH-MATHS CONCEPTS. Please see my other videos also, all the 10 structural analysis videos, and also the videos of engineering mathematics, by IIT Alumni. I am an IIT Alumni, and fluid mechanics. View them, review them, and comment on them so that I can reply. And I prefer, please follow a systematic manner for solving the problems. Don't take shortcuts, and whatever theory you are understanding now, if you thoroughly understand the theory, definitely you will be able to use those concepts in the examination for bettering your performance. Best of luck to everybody. It's again Ramchandra from CIVIL-MECH-MATHS CONCEPTS channel. Please view, review, comment and then please subscribe to my channel so that you will get the regular updates. Subscribe to my channel. I will also be encouraged to provide more and more inputs to you. And by the way, I am planning to write a MCQ book on fluid mechanics and also structural analysis. Please wait for that also. I will be definitely giving the link for procuring that MCQ book, which is being written by me, especially in civil engineering. One topic, fluid mechanics, I want to cover in MCQs. Separate books will be there on each subject. MCQs of fluid mechanics, MCQs of structural analysis. So that I am planning to expand my lectures. Till now fluid mechanics and structural analysis is touched. Maybe in future courses I will go for irrigation. That is also one of the most important subjects which is to be covered in civil engineering. That is one of the major topics which we have to cover. Because of this fluid mechanics and structural analysis, we can go into irrigation, so that environmental engineering. These four are almost interrelated as far as calculations, designs are concerned. Weirs, designing of the weirs, open channels, sewers, designing of the water supply systems, all these are interrelated. So that we can study them. In a systematic manner, I am moving my cards so that you will be able to understand and link one subject to another, and you can avoid the repetition, and you can do the calculations and you can do the questions with due intelligence and confidence, provided you study well the standard books and read my MCQs books and also follow my lectures well. Best of luck to everybody. It's again Ramchandra from CIVIL-MECH-MATHS CONCEPTS. Best of luck.